Well, okay, so, well, thanks for being here again. Maybe you can set off the echo. So what I want to do this morning was first to correct a small oversight I made yesterday. So yesterday I tried to derive from scratch the Lagrangian for the 1pn post-Newtonian expansion at 1pn order, Lagrangian for a point particle at 1pn order. So I wrote a result which didn't show the effect of psi. So if you compare to your notes yesterday, so here I had a phi n, the Newtonian gravitational field. And the reason which I forgot to mention is that at leading order, phi and psi actually turn out to be the same, following from the field equations. This you saw also yesterday in the afternoon, because it also applies in cosmology. Remember that psi is this potential appearing, it's essentially the trace of the metric. And in post-Newtonian theory, at leading order, they are indeed the same, as is the case in cosmology, if you don't have anisotropic stresses. So I thought I would mention this. So I thought it was more useful to write the expression for the Lagrangian in terms of psi, so therefore in this way, because if you do so, you realize that when you take V equals to C, so if you spatialize to null rays or to photons, you see that the order of this psi decreases. So the V over C becomes 1. And therefore, this term appears at the same order as the Newtonian potential. And this is why psi actually appears at 1pn order when you do the post-Newtonian expansion for a massive particle, but actually appears at leading order, so it's one of the dominant terms, when you consider light bending around the sun. So in fact, this was as I mentioned yesterday, the second test of general relativity, which was performed in 1919 by Eddington, who tried to measure the light deflection of stars grazing the sun during an eclipse. So this was not apparent from what I wrote yesterday, so I thought I would just correct it. This is a very minor point. And also, the other thing I wanted to say is that psi in general will not be the same. These two post-Newtonian potential, psi and phi, will not be the same beyond leading order, which again you also saw yesterday in the afternoon. I was told, or in the lecture after mine, when you looked at linear perturbation theory in cosmology, so you had these two potential, exactly the same two potential, phi and psi, and they are different if you have anisotropic stresses in your cosmic fluid. So this was just a small correction to what I said yesterday. So today, what I will be doing will be to derive the quadrupole formula. So I will derive the equation for the generation of gravitational waves. So yesterday we saw we counted how many degrees of freedom there are that describe the gravitational field. We saw that there are just 2 propagating degrees of freedom on flat space and in vacuum. We saw that things are more complicated in curved space and in the presence of matter. In the presence of matter, you have many more post-Newtonian potential, a frame dragging potential, a Newtonian potential, a light bending potential, but you also have the same, and all these three, the frame dragging potential and the 2 post-Newtonian potential phi and psi, satisfy elliptic equations. So they don't entail any propagation of the gravitational field. Where the propagation of the gravitational field is encoded is in the equation for the transverse traceless part of the metric perturbation, which is, as we wrote yesterday, box of ijtt equals minus 16 pi sigma ij, where sigma is the transverse traceless part of the stress energy tensor. So let me see, let me get my notes. Okay, so what we want to do is to solve this equation. So remember that the box operator is the box operator in flat space. for which you know what the green function is. So remember that the green function for the box operator, which is defined by the following formula. So this is just the definition of a green function, of the green function in general, delta 3x xi. So if this is a generic differential operator D, the green function is defined by solving this equation in the sense of distributions. So for the box operator, this differential operator is, of course, the D'Alembertian. And it turns out, as you know from your electromagnetism studies, that the green function is given simply by this expression, which gives you essentially the retarded integral. Minus norm of x. So what does this mean? It means that you can write your solution for chi_ij_tt as a retarded integral, which you can write, therefore, as the integral of sigma ij evaluated at t minus x prime. Sigma will also be a function of x prime. So this is simply a retarded integral. So if you don't remember what the green function is, you can simply open your textbook on electromagnetism and find the solution to the wave equation there. And of course, you can write the solution to any wave equation as a retarded on flat space as a retarded integral of the source with a 1 over x minus x prime term, which would give you a 1 over r fall off far from the source. And so I mentioned that sigma ij is nothing but the transverse traceless part of Tij. So how do you get the transverse traceless part of Tij? Well, what you do, you apply a projector. So you apply this projector, you define this projector Pij equals Kronecker delta ij minus delta j. So let me define this object. So delta ij is, of course, the Kronecker delta. These two are partial derivatives with respect to the I and j coordinates. And this division by nabla squared, which means nothing, is a shorthand for the inverse of the Laplacian. So if you want, I could write it more formally as dij, di dj, now the inverse of the Laplacian. So you can check that this operator, so that if you write sigma ij equals dki l j t k minus p I j p k l t. So I've defined this projection operator, and I write sigma ij as this operator applied to each index of the stress energy tensor, each spatial index of the stress energy tensor, minus this trace part. And you can check that indeed, if you define sigma ij this way, it satisfies the following boundary conditions. So if you apply the derivative and contract with one spatial index, because of the properties of this projector, and if you can just crunch the numbers, and you'll find that the derivative is 0, or the divergence is 0, and that the trace will also be 0. So of course, this, to do that, you need to notice that, well, some basic things. So this this being a projector satisfies identities such as this. So the square of the projector equals to the projector itself. And also this projector has trace of 2. So these are two properties that you need to use to this purpose. So this is a projector, so the square of the projector is the projector itself, and you can check it yourself. Because this is a transverse projector, the trace is 2. You get a 3 from the trace of this object, minus 1 from the trace of these 2. So when you contract I and j here, you get nabla squared, multiplied by the inverse of nabla, so that gives you 1, so the trace is 2. So using these properties, you can prove that this is the expression for sigma ij, for the transverse traceless part of the stress energy tensor, and this is the expression that we need to put in this retarded integral. Okay, so now we want to massage a bit this expression, and we will see how we'll get to a first expression for explicit expression for the solution that we will be able to use. It will not be the final expression, and I will explain why. First of all, yeah, so I have this complicated object, sigma ij, inside the integral, so I would like to simplify that a bit. To this purpose, let me write that retarded integral in a slightly different way. So more operationally, let me define an operator box to the minus 1, which is the inverse of the box, which is nothing but that green function convoluted with the. So I can write this, right? So this box to the minus 1 is simply given by that retarded integral. So it's the inverse. The retarded integral is the inverse of the box. So I've done nothing here. I just divided in a sense by the box. I just taken the box to the minus 1 of the original equation. Then what do? I just write the explicit form for sigma ij, pk I p l j. Let me use the same notation here. So again, I've done nothing. I've just replaced the expression for sigma ij that we just obtained. And now, because this box operator, this is the inverse of the box. The box is the flat space box, as I wrote somewhere there. So partial derivatives commute. So I can commute, and also the projector is defined in terms of partial derivatives. So I can swap these two operators. Well, I'll rewrite the same thing. pki plj minus 1/2 pij pkl box to the minus 1 of tkl. And this is now my retarded integral. So I've swapped, if you want, my retarded integral on sigma ij, which was difficult to handle because of this projector operator. And I brought the projector operator outside the retarded integral. So this then box to the minus 1, what is it? Well, I'll not rewrite the, well, let me actually, because there are some factors, so let me rewrite it here. pki plj, sorry for rewriting always the same prefactor. Actually, let me put a 4 here. Pij pkl, and this is retarded integral of tij evaluated at t minus x prime and x prime divided by x minus x prime d3x prime. So what I've done here is simply to use the fact that I know the green function of the flat space-time, the Lambertian operator, and I just applied it. Then there are some factors. There is a factor 4 pi, minus 4 pi, which cancels with the 16 pi and gives me 4. So now so these projection operators are still defined in terms of derivatives with respect to x. So, and that is a bit, those are, especially the nabla to the -2 operator is a bit difficult to handle. So what I want to do now is to try to simplify this projection operator. So to this purpose, I want to put myself, so this is of course chi ij evaluated at t and x. Whereas the primed quantities x prime are coordinates that cover the source. So I want to put myself in a situation in which I want to evaluate the gravitational wave strain at large distances from the source. So I put myself in a situation in which the norm of x is much larger than the norm of x prime, right? So this means that I'm very far from the source. So if I'm very far from the source, then chi ij dt, I could approximate this x minus x prime in the denominator with simply x. And here also the norm of x minus x prime at leading order would be simply the norm of x. So let me rewrite this. Well, I'm not sure if, well, I'll just rewrite it for EK. It's a bit boring to rewrite the whole thing again, but EKL. And this is now then, because if I approximate this with the norm of x, I can bring this outside the integral. So this becomes 1 over r. Let me denote the norm of x by r, the distance to the origin of the coordinates, and this simply becomes tij t minus r x prime. No, there is no more denominator, and this is integrated over the x prime. Okay. So this is the usual multipolar expansion that you do also in electromagnetism, at leading order at least. So now these projection operators, these partial derivatives, are partial derivatives with respect to x. So x here only appears through r. So x prime is the quantity I integrate over, coordinate that covers the source. And these projection operators, defined in partial derivatives, are derivatives with respect to x, non-primed x, which only appears inside r. And then if you do some more, if you do your calculation, which I will not be doing here, but you should be able to do it at home. It's a calculus exercise if you want. This the Pij defined here, Pij simply becomes delta ij minus ni nj, where ni is simply given, it's the unit norm vector corresponding to x. So because here x only appears through the radial coordinate, when I do derivatives with respect to x, of course, the derivative of the norm of x is simply ni. So using this fact, you can show that all those partial derivatives, in fact, become simply the unit norm vector corresponding to x. If you want to do this at home and don't succeed, come and talk to me. I can show you how to do it. Although it's really just calculus. Okay, well, and, you need to invert the Laplacian for a function which depends only on r. So there are a bit technical. There is a small technical complication, but it's not that difficult to do. But otherwise, this is a. You already see that this is a projection on the space orthogonal to the propagation of the wave. This is why this is called a transverse traceless operator. This is why it's called a transverse projector, because it cuts out anything in the direction of propagation of the wave, which is Ni. Okay, so we have a first result. Let me put this R. In fact, you can put this R here. You can show it leading order when R, so this result is much larger, when R is much larger than 1 in these units, or the mass of the source. You can, in fact, commute the 1 over R also with these projection operators. And you get a first result. So you get an expression for the strain of the gravitational waves, which decays as 1 over the distance to the source. This is the same as the, if you want, the behavior of the electromagnetic field. If you look in electromagnetism at how the electric field decays with radius, with distance to the source, it decays as 1 over R. You get a bunch of geometrical factors which cut off which make the strain transverse and traceless, and you get a source, which is simply an integral over the stresses of the source. So it's an integral over Tij. So now, this is the first result that usually textbooks get. This is not yet the quadrupole formula. And I will explain to you how you get from this to the quadrupole formula. And then I will try to convey why you would be wrong if you thought this was a result that you can already use. So you might try to apply this result to a binary system, and I will show you that it would give the wrong result. So this is not yet the final result. If you were to apply it blindly, it would give the wrong result. And I will explain why it gives the wrong result and why the quadrupole formula instead gives the right result. I guess I can erase this anyway. So if you open any textbook on gravitational waves, for instance, Schutz or any other textbook, they go through a derivation like this, and then what they do is to try to convert this integral over the stresses of the source into an integral over second time derivatives of the quadrupole moment of the source. To do so, they use the conservation of the stress and energy tensor. So here we're doing linear theory over a flat space. So you would be excused to think that this is a good thing to assume. So you blindly, again, you might say, because I'm doing perturbations over a flat space, I should assume that the source satisfies the usual conservation of energy and linear momentum over flat space. Okay, suppose we buy this, and I will explain why it's you probably shouldn't, but this is what textbooks do. You can show that this relation implies this complicated identity, which I will write here, T00, second time derivative of T00 xi xj equals 2Tij plus dk dl tkl xi xj, and there is an extra term here, which is minus 2 tk tik xj plus tkj xi. So it's not obvious that this follows from this. Well, to show it, you need to, well, the best way to do it is probably to expand. You expand these second derivatives. You get derivatives with respect to T00. The partial derivative with respect to xi, and xj doesn't act. So you get second derivative of T00. here, similarly, you expand these derivatives, and then if you use the conservation of the stress energy tensor, you'll get that this is an identity. So it's just a matter of expanding this relation. It's not obvious simply by looking at it, at least not to me. But if you expand these derivatives, you'll find that this implies this. Okay, so once we have this, what can we do? We have Tij here. We have Tij here, so we can express Tij in terms of second time derivatives of t naught naught xi and xj plus total derivatives. So if you want, you can write d3x prime Tij t minus r x prime, and this becomes an integral over 1/2 what is it, 1/2 t00 t minus r x prime, and this is x prime I x prime j d3 x prime plus surface terms. Right. So these total derivatives here, when you do the volume integral, these are total derivatives, so they give you surface terms, which will go to 0 because the stress energy tensor of the source will be 0 at infinity. So you can use Gauss' theorem to transform them into surface terms, and you can discard them safely. And this is how you go from an integral over the stresses of the source into an integral into the density of the source. T00, I remind you, is essentially the density of the source, multiplied by xi and xj. So this is very similar, if you want, to the moment of inertia. Remember that the moment of inertia is the integral of rho x squared in d3x. So here we have a tensor instead. We have xi xj d3x, and this is what we call the quadrupole tensor. Yeah, in fact, this is, let me put the quadrupole tensor. Okay. So in the end of the day, when you account for all the factors, etc., what do you find? Let me write the final result. Chi ij tt equals, well, I get a 4 over r that I was getting there. Yeah, 4 over, actually, yeah, because there is a 1/2 there, I get a 2 over r. Then I get the second time derivative of I, let's call it k l, and then I have these projector operators, which are p I k p, what is it, j, what is it called, l minus 1/2 p k l p I j. And here I have also a factor. If I reinstate the g's and the c's in the calculation, which I've neglected so far, I get a g over c to the 4. And so these projector operators again are defined in terms of the directional propagation of the wave. And this I k l is again defined in terms of integral of d3 x prime rho, it will be t minus r x prime x prime I x prime j. So now the last, sometimes in books you also see a similar expression where this I is replaced by the traceless part of I. So you sometimes find this expression I k L minus 1/3 delta k L, and this will be the trace of I. So here you can have an expression in terms of second time derivatives of I, or you could have a similar expression in terms of second time derivatives of the traceless part of I. They are completely equivalent because this trace term is actually killed by these projector operators. And the reason why in books sometimes you find the expression in terms of this traceless part of the quadrupole tensor is that you want to highlight the fact that physically only the traceless part of the quadrupole tensor produces gravitational waves. So if you have a spherical body whose moment of inertia changes, but there is no anisotropic part, then you don't produce gravitational waves. Okay, so this is the textbook derivation of the quadrupole formula. Probably some of you have seen this already. How many have seen this already? Okay, maybe 30%. Okay, so you can come to me if there are some technical passages. The only, I think, difficulty, or it's not really a difficulty, but it's to show how partial derivatives become derivatives with respect to the direction of propagation of the wave. However, so we've done all this. So what have we done? I want to summarize what we've been doing so far from a more conceptual point of view. So what we have done is to start, remember, from linearized theory over flat space. So we started with g mu nu, if you want, equals eta mu nu plus a perturbation, which we then decomposed in several parts according to scalar parts, vector part, tensor parts, and in particular we solved for the tensor part. So if we have linearized theory over flat space, then we're justified to assume that the stress energy tensor is conserved, covariantly conserved, where the partial derivatives appear in the conservation law. And then what we did was to use the Green function for the transverse traceless part to find the quadrupole formula. So one problem with this procedure is that this equation, conservation of the stress energy tensor, if applied to particles, actually implies that the acceleration of a particle is 0. So why is that? Well, so what is the stress energy tensor for a particle? You could derive it formally. So you remember yesterday we wrote the action for a point particle. And in principle, let me get my notes so that I get all the factors right. You could use the usual definition of stress energy tensor, which is given by, in terms of functional derivatives of with respect to the metric, to derive stress energy tensor for a particle. So you could take this action. Notice that in the proper time, remember, is defined as square root of g alpha beta dx alpha dx beta. So you could, and in fact, you could write this as in the following way. So you could now take the variation of the action with respect to the metric. The metric only appears here under the square root. And if you do a little bit of algebra, which I could do, but I don't know if it is worth spending 5 minutes on this, you find that T mu nu is given by the following expression. If you just take the usual definition of stress energy tensor in GR applied to a point particle source, you find the stress energy tensor of a particle, which is given by some density. So this this Dirac delta is essentially the density of the particle multiplied by the mass. Then you have some geometric factors having to do with the reference frame with respect to which you define the density. And you have the forward velocity of the particle. So this looks very much like a fluid of dust. You remember in, I'm sure yesterday or at some other point in your studies, you will have seen the stress energy tensor for a perfect fluid. Did I get the sign correctly? Probably not. Yeah, like this. So this is the stress energy tensor for a perfect fluid. You've seen it in cosmology, certainly. If you set the pressure to 0, you get dust. So rho u mu u nu. So this is essentially the same as the stress energy tensor for a point particle once you identify the density with this object here, which of course makes sense because you can think of dust as a collection of particles. So now you probably you have seen it yesterday or again from when you took your GR course that the conservation of the stress energy tensor in generic on a generic curved background implies in particular the relativistic Euler equation that which is given by something like this, h mu nu, so let me call it a different way, gamma mu nu gradient of p divided by p plus rho, where this gamma is a projector operator orthogonal let's see, minus u mu. Mu, I get a minus, yeah, so it's, right. So when you took if you ever took a relativistic hydrodynamic course, you will have seen that the covariant conservation of the stress energy tensor for a perfect fluid implies energy conservation on the one hand, and on the other hand, a relativistic version of the Euler equation, which is given by acceleration equals the gradient of the pressure divided by p plus rho. And this gamma is a projector on the direction orthogonal to the forward velocity. So if you contract gamma with forward velocity, depending on your signature, if you use a minus plus 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 signature, you get a minus 1 here, you get a u here, and so you get that this projector applied to the forward velocity gives you 0. So why am I telling you? How many of you have seen this? Euler equation, relativistic Euler equation? No one. Well, few. You can try to derive this if you want. You can just take this ansatz for the stress energy tensor of a perfect fluid, insert it here, expand the covariant derivatives, and then take the spatial part of that. You will find exactly this. You will find exactly this relativistic Euler equation. So why am I telling you all this? Because I've just tried to convince you that the stress energy tensor of a point particle is the same as the stress energy tensor of dust. dust is a particular version of a perfect fluid with zero pressure. Therefore, for dust, this for acceleration would be zero, because I set the pressure to zero. So what I'm trying to convince you, in fact, is that, and in particular in the flat space-time case, conservation of the stress energy tensor of a fluid of dust or a fluid of point particles implies that these point particles or this dust follows geodesics of the background space-time. So this is in fact true in any space-time, but in particular it's true here in flat space. So conservation of the stress energy tensor of the point particles on flat space implies that those particles must follow geodesics of flat space. And geodesics of flat space are straight lines, of course. If you move along a geodesics of Minkowski space, that's simply a straight line. So why is this a problem? Because we want to apply this result that we obtained for the quadrupole formula. Eventually, we want to apply it to binary systems. Binary systems move on circles, so they're clearly not straight lines. So this is, if you want, a conceptual problem that we have to face. So gravity in a binary system is not weak, because if gravity were weak, the component of the binary system would follow straight lines. They would never circle one around each other. So if you want this, let me get this. Straight lines. Straight. You spell straight this way, yeah. Lines. So if you want, we made so if you want, the whole derivation that we did is good for textbooks, but it's not very rigorous. And you might think, well, who cares? But actually, you should care, and I learned this a few years ago. I was trying to, I think I still have the formula. I was trying to use this formula that we wrote for the gravitational wave strain in terms of integrals of Tij. So what did I do? I just took a binary on, let me keep this. So I consider a binary, mass is M1, same mass, let's call them, yeah, let's call M1, M2, but then I will specialize to. I consider a binary on circular orbit, moving of, so M1 and M2 are the same, M1 equals M2. So the system will, I consider a circular binary, so it will move around the center of mass, and the frequency, the orbital frequency of this system will be given by Kepler's law, Gm over r to the 3. So m is m1 plus m2, and r is the separation of the binary. So I just consider Newtonian theory, a binary moving around the center of mass. And what I did, I wrote, or what you can do as a simple exercise, is to write x1 I, so the position of the first binary, that will be given essentially by what, r half cosine, yeah, let me write as a vector, cosine of omega t plus a phase, r over 2 sine omega t, and then I choose coordinates adapted to the plane, so the third coordinate is 0. Then I'll have x2i equals minus x1i, etc. So you can try to insert this formulae in either this expression. So remember Tij, well, Tij will be given by that formula. So you'll be able to compute what Tij is once you know the forward velocity of your particle. And you can insert the same expressions in the quadrupole formula that you derive in textbooks. Yes, so this I can erase. and you get different results. In fact, you get a factor 2. Let me write the result for you. So consider now, so I consider this binary in the x binary on the x, y plane, and I consider a gravitational wave propagating in the z direction, so orthogonal, if you want, to the plane of the blackboard in z direction. And what you get is that chi ij tt equals, let me call this, I don't know, a, some amplitude, multiplying cosine 2 omega t. Yeah, here I get a minus cosine 2 omega t sine omega t, sorry, sine of 2 omega t, sine of 2 omega t, 0, 0, 0, 0. So both the quadrupole formula in terms of second derivatives of the quadrupole moment and this formula in terms of integral of over the stresses, they give you a dependence on, if you want, a harmonic dependence on twice the Keplerian frequency. So they both give you this matrix, but this amplitude here differs by a factor 2. In particular, A, given by the quadrupole, which is the correct result, as I will try to explain, will be given by 4, the reduced mass of the system, which, well, in our case, it's an equal mass system, but I'm writing the formula for the generic case, omega squared. This is the big R. Sorry, yeah, I call that the separation of the binary, I called it small r, so the amplitude given by the quadrupole formula depends on the square of the Keplerian frequency times the separation of the binary squared divided by the distance to the source. And the green, by green I mean this formula in terms of integrals over stresses is different by a factor 2. I don't remember in which direction. Different by a factor 2. If you don't believe it, you can do it yourself in mathematics or by hand. So there are several things to be brought home from this exercise. One of the most obvious is that even if these two formulae, they differ by the amplitude, well, they still give you the structure for this tensor, which is the same as the one we saw yesterday. So yesterday I mentioned that for a wave propagating in the z direction, you have a structure like this, in which you have this is the first thing I showed yesterday. You have two polarizations, the plus and cross polarization. The plus polarization appears on the diagonal with opposite signs, because the trace of the gravitational wave should be 0. This is why it's called transverse traceless perturbation. So in fact, here you see cosine and minus cosine. And then you have a cross polarization on the off-diagonal terms. And you have no component in the direction of propagation of the wave, in the z component. The other thing you can notice is that if the binary was moving at frequency omega, called it Keplerian, the frequency of the gravitational wave is twice the orbital frequency. So this is in general true at leading, well, to first approximation. Omega gravitational waves is given by twice omega orbital. And this is due to the fact that gravitational perturbations, the gravitational field is a spin 2 tensor. So it has to do with how the gravitational field transforms under rotations. The other thing to bring home is that we need to assess which one of these two formulae, the quadruple formula that we got in the end, or the intermediate result that we obtained, is the correct one. And this is what I will explain now. It's not a trivial thing, not a completely trivial thing. Sometimes you find this hinted at in textbooks. So sometimes in textbooks you read that the derivation of the quadruple formula is not correct, and you have two mistakes cancelling one another. And the two mistakes are, again, the fact that we use linear theory, which is wrong, and the fact that we assume propagation over we assume motion along straight lines, which is also wrong. And somehow these two errors cancel each other, and as a result, this quadruple formula is the correct one, and this green formula is the wrong one. But it's how in detail they cancel each other is usually not explained in most textbooks. So I will try to give you the answer here. So are there any questions at this point? Is this all clear? No questions. I'll erase this. So I want to give you now a more rigorous derivation of the quadruple formula, which will make clear, which will not have the flaws that I just described. So it will not assume weak field. It will not assume that we linearize over flat space, and will not assume that the source moves along straight lines. So if you want to go beyond linear theory, well, you have to use the full strength of the Einstein equations, I'm afraid. And those can be complicated. There is, however, a very nice way of writing the full Einstein equations, which is called relaxed form of the Einstein equations. Relaxed form of Einstein equations. So what you do is to introduce an object. Even though it has two indices, it's not a tensor. Let me call it h bar, mu nu. It's a pseudotensor, in fact. Pseudotensors have a bad name in usually textbooks don't talk about them, but I think they're very useful for understanding well, they're very useful for many things. So this h bar mu nu is given by the Minkowski symbol, eta mu nu, minus the square root of minus g times g mu nu. So this combination here is sometimes called the Gothic metric. So I can't type on the blackboard in Gothic form, but sometimes in the early, when you look at early articles about GR, this was very popular, and it's indicated with a G with a Gothic font. So this is not a tensor; it's a pseudotensor. It's not a tensor because this is not covariant under generic coordinate transformations. The square root of minus G is not covariant under generic coordinate transformations, but still you can use it. Let me also use the gauge freedom that I have in general relativity to impose this condition, alpha beta equals 0. And this is sometimes called the harmonic gauge. This is also not a covariant coordinate condition. It's not a covariant gauge condition, but I'm still allowed to choose my coordinates such that is verified. So if you do so, the full Einstein equations with no approximation, no nonlinearity whatsoever, take the following form: alpha beta minus 16 pi tau alpha beta. So these are the full Einstein equations. These are equivalent to g mu nu equals 8 pi T mu nu. So I'm not making any approximation whatsoever. I'm not considering flat space, or this is the flat space-time box. But still, I'm not making any approximation. I'm not assuming space-time is flat. This just turns out to be the flat space-time box operator because I introduced this object h, which is defined in terms of eta. That's why that flat space-time box operator appears. So this would seem deceivingly simple, except that this object tau AB is not the usual stress energy tensor. It's actually given by a very complicated form, which I'm not sure if I should write. I'll write part of it. So tau alpha beta is given by minus g, the determinant of the metric, multiplying T alpha beta, the stress energy tensor of matter, plus an object which I will call lambda alpha beta divided by 16 pi. So what is this object, lambda alpha beta? It's 16 pi minus g, this object, this pseudo-tensor called sometimes the Landau-Lifshitz pseudo-tensor, T alpha beta LL, for which I will not give you an expression, plus, and this I need to write, h bar alpha mu comma means partial derivative, of course, h bar beta nu comma nu minus h alpha beta comma mu nu h bar mu nu. So I have to speed up a bit, I think. Well, so I will not give you an expression for this Landau-Lifshitz pseudo-tensor. You can, I can give you my notes if you want, because it takes several lines. But this is quadratic in h bar. So it involves terms which are quadratic in h bar or in the derivatives of h bar. And I chose to write this term because this term actually involves second derivatives of h bar. And this is just, well, I don't know if you'll appreciate this fact, but this shows you that the principal part of the equations is not the flat box. So usually in general relativity, when we talk about the principal part of the equations, we mean the second derivatives. So the second derivatives are not given simply by second partial derivatives, but there is a term here which is crucial for the propagation of the waves. Well, if you don't know what the principal part of a system of partial differential equation is, forget about this comment, but it's important to remember that second derivatives are not only given, there are also nonlinear terms in the second derivatives. Okay, so why am I telling you all this? Because now we get the full Einstein equations, g mu nu equals 8 pi t mu nu, written in a very convenient form. In particular, we get an equation which when, so in particular, the other thing that you can notice is, oh yeah, sorry, before I go on. So these are the full Einstein equations, okay? And then I can take the divergence of this term here, and I can take equally the divergence of this term here. So I can take the partial derivatives with respect to alpha and contract. Then my partial derivatives will commute with the box operator. They will be applied to h bar, and the divergence of h bar is 0 because of the boundary conditions. So by taking the divergence of these equations, what you'll get is that T alpha beta comma alpha is 0. So we have yes, so let me. So we have on the one hand this equation, which is equivalent to the full Einstein equations, and which looks very much like the equations that we looked at yesterday. And we also get the conservation of this pseudo-tensor tau, which includes a contribution from matter and from the gravitational field, which is conserved with respect to the partial derivative. So now I can take this equation and apply exactly the same procedure as there, as in the first part of my lecture. So I can invert the box, apply it to tau alpha beta, so I can find the solution for h bar in terms of retarded integrals, right? And if I do so, I will find the same quadrupole formula that I found before. So I will find that h bar, if you want alpha beta, can be given either by the second, well, up to factors which I don't want to write, second time derivatives of tau 0, 0, xi, xj, d3x. And it's also proportional to the integral of tau ij d3. Sorry, this will be x alpha beta j. Or in particular, if I look at the spatial part, let me write it in terms of the spatial part. Tau ij d3x. So I can apply the same procedure that I did in the first part of these lectures to derive the spatial part of hij. And I can write that spatial part of hij either in terms of second time derivative of this newly defined quadrupole tensor, or in terms of integrals over the stresses, right? And why is this useful? Because this h bar ij is actually the gravitational wave. Because if ij is in linear theory, so if I say that g mu nu equals eta mu nu plus h mu nu, so if I take this expression, replace and g with a perturbed Minkowski metric, this turns out to be the same trace-reversed metric perturbation that we derived yesterday. So this object h bar in linear theory reduces to the trace-reversed metric perturbation that we saw yesterday. You can try and just expand the square root of the determinant, and you will find that this is exactly the case. So we now found that this h bar ij, which is actually the same as the trace-reversed metric perturbation, is either sourced by second time derivative of the quadrupole of this quadrupole moment or the stresses. And then we need to relate that tau alpha beta with the stress energy tensor of matter. So if you take this full expression in terms of the Landau-Lifshitz pseudo-tensor, you'll find that tau 0, 0 is given by T00, the stress energy tensor of matter, plus corrections, which are negligible in a post-Newtonian expansion. So you perform a post-Newtonian expansion of that expression. So you include all the factors C, as we did yesterday in the post-Newtonian expansion for a point particle Lagrangian. And you Taylor expand in 1 over C. And you find that tau 0, 0 is the same as T00 0 at leading order. But tau ij is actually not. Tau ij equals Tij plus terms, which I need to copy because I don't remember by heart. 1 over 4 pi di dj phi minus 1/2 delta ij dk, well, this is just the gradient of phi squared. And this is plus corrections of order 1 over c to the 2. Yeah, so at leading post-Newtonian order, tau 0, 0 corresponds to t 0, 0, whereas tau ij is not the same as tij, but it has corrections which depend on the Newtonian gravitational field of the binary. So if you want to use the expression for the gravitational wave strain in terms of integral over the stresses of the source, you need to be careful because the stresses of the source are not only given by the stresses of matter, but also they are also given by the stresses of the Newtonian gravitational field, if you want. And in fact, you can show that this term here, this additional term here, corrects the factor 2 difference that I mentioned earlier. So this is why, if you want, you need to use the quadruple formula and not the formula in terms of the integrals of Tij, because if you were to use that formula, you would have to include the contribution from the gravitational field. So this is, if you want, the real derivation of the quadruple formula. So in the end of the day, this is the formula. In the end of the day, gravitational wave strains are sourced by the second time derivative of the quadruple. So in the last half an hour, I want to do something to derive very quickly the stress energy tensor of gravitational waves, because you used this yesterday in an exercise. So I wanted to give you a quick derivation of that. So are there any questions on the quadruple formula on this second part? No? Okay, so now we derived the formula for the gravitational wave strain, the quadruple formula, but we haven't shown yet that gravitational waves carry energy and angular momentum. Well, actually, in a sense, we expect it from this expression. So I mentioned that the gravitation, that on the right-hand side of these relaxed Einstein equations, there is this object, tau alpha beta, which includes a contribution from the gravitational field. So in a sense, in particular, this Landau-Lifshitz pseudotensor plays the role of the stress energy of the gravitational field. So we already see from here that the gravitational field should carry energy and angular momentum. However, a more convenient or a simpler way to get the same result is to use the geometric optics approximation. So consider a space-time with some curvature radius L. So this is, if you want, a one-dimensional space-time. So this L could be due to this curvature radius could be given by the gravitational radius of a black hole. So this could be the mass of the black hole, for instance. And consider a small gravitational wave, or a gravitational wave with a small wavelength, moving on this space-time. So the wavelength of the gravitational wave would be much less than the curvature radius of the background. And of course, you could write this as, again, this equals a background space-time plus a small gravitational wave. So you can rely on separation of scale to separate the background, which has some curvature radius, L, from the small scale structure given by the gravitational waves. This is what we call the geometric optics regime, if you want. So what I want to do is now to decompose the metric for this space-time as a background metric, G alpha beta, and let me call it B. B stands for background, plus perturbations due to the gravitational wave. So this epsilon again is a perturbative parameter which is of order lambda divided by L, plus epsilon squared, so if you want, epsilon squared, plus second order perturbations, which I will call J alpha beta. Plus, of course, there will be higher order terms in this expansion. So what am I doing here? I'm doing, if you want, I'm relying on the separation scales to separate the gravitational wave from the background, and then I'm doing a perturbation over the, if you want, the strain of the gravitational wave. Yes. So now what I want to do is to expand the Einstein equations in epsilon. Actually, sorry, so I think I was incorrect here. So this epsilon, so I rely on lambda much less than L. I can split background and gravitational waves. And here on top of this, I assume that the perturbation due to the gravitational wave is small. So this epsilon parametrizes, if you want, the amplitude of the gravitational wave. Sorry about this. Parametrizes gravitational wave amplitude. Okay. So in practice, the two are connected because when if you look at the quadrupole formula, the frequency also appears in the quadrupole formula. But anyway, so it's useful to think of epsilon and the geometric optics approximation as two separate expansions. So now I want to consider the Einstein equations in vacuum. So these are Einstein tensor equals 0. And let me write the Einstein tensor. Let me expand the Einstein tensor in epsilon. So I first get the Einstein tensor applied to G background. This is the background. So I just take this perturbative expansion for the metric and replace it in the Einstein equations. So at 0th order in epsilon, I get simply the Einstein tensor calculated from the background. Easy. Epsilon H and G background. So this is just a cartoonish way of saying that here I expand in the Einstein equations, and this is the first order term, which will depend on the perturbation H, will be linear, in fact, on the perturbation H, and of course on the background metric. Plus I will have second order terms, which will again, which I will call G2, be second order terms from J, and from there will also be second order terms from, sorry, this is G1, G2. There will be second order terms coming from H, GB. What am I meaning by this expansion? So at first order, okay, I have terms which are linear in H. At second order, I have terms which are linear in J. This is what I mean here. So this operator G1 is linear in H. But I can also get second order terms by first order perturbations multiplied by themselves. This is what I mean by G2. So this G2 means that this operator is quadratic in H. So this is just a usual complicated way of writing the usual perturbative expansion. When you go to second order, you can get second order terms from squares of first order perturbations, or you can get second order terms from the second order part of your metric. So far I've done nothing but writing the Einstein equations, so you can calculate explicitly what these terms are if you have a sufficient time. And then what I want to say is that, and here of course there will be higher order terms, order e to the epsilon to the 3. And now I want to solve the Einstein equations order by order. So I get first at 0th order, if I set epsilon to 0, I get g alpha beta for the background equals 0. These are the Einstein equations for the background. Then I get, at first order in epsilon, I get that this term should be 0. So g1 of h gb equals 0. And then at second order, I get that g1 of j g background equals minus g2 of h g background. So I've done nothing but setting to 0 each of these terms. So I set the first order terms to 0, second order terms to 0, and so on and so forth. So far I've done nothing, so you can again calculate what the equations are at first order, second order. At first order, of course, what you'll get will be something in a suitable gauge. You'll get the equations that we wrote yesterday. What was it? Box h mu nu plus 2 Riemanns. I don't remember the indices, alpha, beta. You get something like this. So if you were to write this explicitly, you will get modulo signs that I might have got wrong. So these first order equations would be exactly the equations we wrote yesterday in our first lecture. And at second order, you will get some more complicated equations. So now what we want to do is to take some spatial average, or space-time average actually, of these equations. So in particular, we want to average over, I will call this, I will use these two brackets to denote an average over regions of the space-time of size much larger than lambda, the wavelength of the gravitational perturbations, but much smaller than L, the curvature radius of the background. So I want to average over a few gravitational wavelengths, if you want, right? So what happens if I do this average? Well, this equation will not change. This is the equation for the background, which is constant on scales much smaller than L. So if I take the average of this, nothing will happen. So if I take the average of this equation, so let me erase this part. If I take the average of this equation, what can I do? So I mentioned that this G1 means a term which is linear, an operator, a differential operator, which is linear in H. So because it's linear in H, I can commute the average with the operator. So this will become G1 average of H, GB equals 0. But then the average of H, so H is this wave. So H will in general be a cosine or a sine of 2 omega t, as we saw before. So if I average over many periods, the average of H will be 0. So this equation will be trivial when I take the average, because this H average will be 0. And this is simply because, again, at linear order, I can commute the average with the differential operator. So this equation here is more complicated. So first of all, I can, if I take the average of the left-hand side, I can commute the average with the operator. So I get the average of J. It's not obvious at this stage what J is. So let me keep it indicated. And then I have to take the average of this second term. Right. And this term is quadratic in H. So I can't simply swap the average with the differential operator because it's a nonlinear differential operator. So what do I want to say here? Okay. So what I want to say here now is so we concluded that this equation is trivial, so we don't care about this equation anymore. Let me write on the other side. Maybe I can write here. Yeah. So we get G alpha beta. So the first equation was the equation for the background. Beta equals 0. And then we have this equation for G1 average of J, GB equals minus average of 2 H, GB. And now I want to sum these two. So if I sum these two, of course, I have that G alpha beta GB plus 1 average of J GB equals minus, of course, G2. I'm doing nothing but summing. Sorry for the trivial passage, but okay. So now, what this is, if I look at this equation, so this was the full G alpha beta, which was given by a background part, a first order part, etc. So what I get here is that the left-hand side is simply, did I get this right? Yeah. And of course here there is an epsilon squared. Sorry, I forgot. Here an epsilon squared, and here there is an epsilon squared, because this equation carries an epsilon squared. So G alpha beta, I can rewrite this as G background plus J, which in turn is G alpha beta applied over the metric, averaged over, again, a few wavelengths, equals minus, and let me write this in a better way, 8 pi T gravitational waves alpha beta, where this T gravitational waves alpha beta, well, it's minus 1 over 8 pi G, or 8 pi, that epsilon squared, the average of G2 H G background. So what have I done in the end of the day? So I was able to write the original Einstein equations. I've rewritten them in terms of the Einstein equations for the metric G averaged over, again, a few wavelengths. So this is an average over a region of size much larger than the wavelength of the gravitational wave perturbation, but much smaller than the curvature radius. So this is the usual Einstein tensor for G averaged, equals some terms which are quadratic in H. So if you want, the physical meaning of this term is the back reaction of the gravitational waves on the background. So these terms will be derivatives of h squared. So in the field equations, when you expand them to second order, there will be derivatives of h squared, which when you average will not give 0. So if they were linear, they would average to 0, but because they are quadratic, in general, they will not average to 0. If you have a cosine, if you average it over several periods, it gives you 0, but if you have cosine squared, if you average, it gives you 1/2. So for those of you who are cosmologists and heard about the back reaction of cosmological perturbations at second order, or back reaction of cosmological perturbations during inflation, this is exactly the same thing. So it's the back reaction of the second order perturbations on the background. So how do you, and we interpret this again as stress energy tensor of gravitational waves, but it only makes sense to talk about the stress energy tensor of gravitational waves if you consider scales which are much smaller than the curvature radius of the background and much larger than a wavelength, than a few wavelengths of the gravitational perturbations. And this is a very deep finding. I mean, it's related to the fact that it's in GR, there is no unambiguous way to define the energy of the locally, to define locally the energy of the gravitational field. I talked before about the Landau-Lifshitz pseudotensor. So I mentioned that it's a pseudotensor and not a tensor, and this is related to this point. You can always find locally a coordinate system in which the Landau-Lifshitz pseudotensor vanishes. So it doesn't make any sense in GR to define the local energy of the gravitational field. It only makes sense to define the energy when you average over a large region of space. So, I still have 10 minutes, good. So I wrote this expression, this diagrammatic expression. So it remains to compute what this operator G2 is and to perform this average. So for, you're lucky I don't have time to do it. And also I didn't prepare notes because it's can be a complicated calculation, but essentially it's again just a matter of expanding the Einstein equations to second order, or as I mentioned there, to expand the Einstein tensor to quadratic order rather than to linear order, and then take an average. And then what you need to do is to perform some commutations between covariant derivatives using the Riemann tensor, and then use again the fact that lambda, the gravitational wavelength of the perturbations, is much smaller than L, the curvature radius, and you can neglect some terms. So this, if you're interested, it's done in quite detail in Misner, Thorne, and Wheeler, Gravitation. But if you want really to understand how it is derived, you can do it yourself in Mathematica. If you know how to use Mathematica, it should be possible. And the final result that you get for this stress energy gravitational, alpha beta, again, it's defined by that formula. It's 1/32g, and then there are the covariant derivatives with respect to the background. So B means background. Alpha h dt rho sigma background beta h dt rho sigma. And this is again an average over several gravitational wave periods. So as I mentioned, this term is quadratic in the second derivative, sorry, quadratic in the first derivatives of the gravitational wave perturbation. And yeah, it looks very much like what you would expect for the energy of a perturbation. This looks like the kinetic energy for your field. So this is one way, probably the simplest way, or one of the I find it the clearest way to derive the stress energy tensor of gravitational waves. And why clearest? Because it, again, emphasizes the fact that you can't locally define the energy of the gravitational field. There are other ways in which you can derive the stress energy tensor of the gravitational field if you don't find this clear. I'll not do it here, and I'll just give you the references. One of them is to use the Landau-Lifshitz pseudotensor that I mentioned before, if I find where I wrote. Well, anyway, sorry, I had it somewhere. One way is to use the Landau-Lifshitz pseudotensor. So you can, so as I mentioned, you can, if you expand this object h bar mu nu that I introduced before in linear theory, that is essentially the gravitational wave strain, the trace reverse metric perturbation. So you can expand the Landau-Lifshitz pseudotensor to in linear theory, and you will find exactly this expression for the stress energy tensor. There is also another way. Let me see if I find the expression, which, if you're a field theorist, you'll find perhaps more clear. Where the hell? Yeah, here it is. Another way of deriving the same result, I think it's safe to, well, I can erase that one. Another way to do the same expansion is to start from the Einstein-Hilbert action. So if you start with this, and then you write G mu nu equals G mu nu background plus a perturbation. And in particular, if you take this perturbation to be the transverse traceless perturbation for simplicity, and you expand the action to quadratic order, you'll find that up to boundary terms, this action becomes d4x over 2, 1 over 32 pi g minus the h dt ij dk h dt ij plus, sorry for h dot tt ij h dot tt ij. So essentially, if you expand the Einstein plus boundary terms, which are, of course, well, in this, I mean, in classical general relativity are not important, and you can set them to 0. So what you find is, if you expand the action to quadratic order, you'll find that the action for, or the Lagrangian, if you want, Lagrangian density for the gravitational wave satisfies, well, it's given simply by this, is quadratic in the derivatives, right? So this looks very much like the action, for instance, for a scalar field. It looks like grad phi squared. So what you can do now, if you remember how you derived the stress energy tensor for a scalar field, well, there are many ways in which you can derive it. One way in which you can derive it is through Noether's, or you can write, if you want, a canonical tensor, which is often used anyway. So you can write the stress energy tensor as, remember, if you have fields, let me call them phi r, you can write the stress energy tensor in this way, phi r, what is it, the derivative of the Lagrangian with respect to I don't know if any of you have seen this expression. This is the canonical expression for the stress energy tensor. You can use it for the electromagnetic field, for a scalar field. In general, it doesn't give you a symmetric stress energy tensor, so you need to add a term to make it symmetric. And this phi r are all the fields that are contained in your Lagrangian. So your Lagrangian density would be function of phi r and derivatives of phi r. So you can do the same here. So your fields are h, the h's. The role of the index r is given by the two indices I and j. So you can construct a stress energy tensor from this Lagrangian density, and in the end you will get the same result. If you're more interested in this, look at Maggiore. There is a book called Gravitational Waves, Maggiore Gravitational Waves, volume 1, or even better, there are some notes by Ed Bershinger at MIT, and I'll give you the reference if any of you is interested. MIT.edu at Bert, I think it's gr7.pdf, and it's very nice because he also talks about the Landau-Lifshitz pseudotensors and so on. And as you've understood, I like pseudotensors. So the last 5 minutes, I just want to make the connection with what Andrea did yesterday on the blackboard. So now we have an expression for the stress energy tensor of gravitational waves. We have the quadrupole formula. So in principle, we can apply the quadrupole formula to a binary system of compact objects, such as 2 neutron stars or 2 black holes, and compute what is the energy lost lost by the system in gravitational waves, because we know what the stress energy tensor is. And what you find is that, I want to say a couple of things. You can write that the luminosity of the quadrupole luminosity of a gravitational wave emitting source is 1/5 g over c to the 5 third time derivative of the quadrupole squared. This is in fact the traceless, what I called before I tilde, the traceless quadrupole squared, essentially. So just to give you the orders of magnitude, just using dimensional analysis, you can write, remember the quadrupole is the mass times the size of the system squared. So I triple dot, or I tilde triple dot, it's the same, is given by mass size of the system squared divided by time scale to the cube, which in turn, again at dimensional, just the orders of magnitude, is given by the mass of the system, the velocity squared divided. So what does this tell you? That if you want to have an abundant production of gravitational waves, what do you need? You need small time scales or very large systems or very large masses. And why do you need such very large masses or small time scales? Because the luminosity is suppressed by this number here, which if you compute, if you're in I don't know how many astrophysicists there are, but astrophysicists like CGS units. In CGS units, this is, I computed, is 10 to the minus 59. So you have this very small prefactor, and therefore you need very large masses or very large systems or very small time scales or very large velocities, if you want, to produce gravitational wave in a very copious way. So in particular, so this gives you, if you apply to this luminosity to a binary system, the luminosity in gravitational waves at the quadrupole order is given by, this is a famous formula that dates back to Peter and Matthews in the 60s, g over c to the 5, g m1 m2 divided by r squared. R, so I called the separation, I called it big R, I don't remember. So this R is separation V squared. Did I get, no, sorry, I got square here. So as you can see, the distance of the source doesn't enter. Why doesn't it enter? Because we saw that the stress energy tensor is, I deleted now the expression, as quadratic in H. So T gravitational waves goes as 1 over the distance to the source squared. And when you integrate over a sphere, this cancels out. So the flux will be given by T, or if you want, rho gravitational waves, integrated over 4 pi, essentially multiplied by, by the volume of the sphere, 4 pi d squared. So this d squared cancels with the volume of a sphere. So this is the flux of the luminosity of gravitational waves. So it's rho multiplied, there are c's here, I'm setting c to 1. So if you want so if you have a source, the flux of gravity, well, I can't draw things in 3 dimensions. Well, this is the usual flux formula that you have also for the electromagnetic field. So the last thing I want to say is that this is the luminosity for a gravitational wave system. The thing that Andrea showed yesterday is that you can use, I think he showed that you can use the balance equation. So you can say that the luminosity, so the energy or the power lost in gravitational waves Q, must be equal to the energy loss by the source. So this E thought is the total energy of the source, which in general will be given by the sum of, in the reference system of the center of mass, it's the kinetic energy. So 1/2 the reduced mass V squared minus G mu M over the separation, which I called R. So, and of course, whatever goes away in gravitational waves must be compensated by an equal loss of energy by the system. So if you use the virial theorem, this gives this energy E total is essentially minus G mu M over twice the separation for a circular binary at least. So I'm assuming here for circular binary. And then you can take the derivative of this energy and you get here a derivative with respect to R. So if you do the calculation, which I've not time to do now, you'll be able to relate R dot to the luminosity in gravitational waves. So you just take the derivative of this expression, you get derivatives with respect to R, you equate those to this flux, and you will find that a binary system shrinks. So the radius of the binary shrinks, and this is easy to understand because as the shrinks, the total energy becomes more and more negative, which compensates for the energy that you radiate away in gravitational waves. And finally, the very last thing that I want to say is that you can use Kepler's law, and remember that F gravitational waves, we said before, is equal to twice the orbital frequency of the binary, because the gravitational field is a spin-2 field. And this F orbital is what? F orbital is, what is it, omega divided by 2 pi. And in turns, omega is given by Kepler's law, omega orbital is given by Kepler's law. It's the square root of Gm over r to the 3. So you can relate, the orbital. So if you want, you can relate, so this will be some function of r. Well, it will be, exactly what I wrote there, Gm over r to the 3 over 2 pi. And then you can relate, therefore, r dot, say r dot equals dr by df gravitational waves times f dot gravitational waves. And you can write this, and you can write f dot gravitational wave, how the frequency changes under the effect of gravitational waves. And what you get is the formula that I think Andrea used yesterday, phi c to the 5 g to the 5/3 pi 8/3 f gravitational waves to the 11/3, and this is the chirp mass that you calculated yesterday. So the chirp mass is big M times mu divided by m to the 3/5. So again, from the stress energy tensor of gravitational waves, you compute how much energy you lose, what is the luminosity. You equate that to the loss of energy of the system. You calculate what r dot is. R dot is negative. You convert this r dot into a rate of change for the frequency simply using the chain rule, and you find that f dot is given by this expression. This is an important expression from a practical point of view because it tells you that at leading post-Newtonian order, the only quantity that you can extract from gravitational wave observations about a binary system is this combination of the masses, the chirp mass. So this is the quantity which is easiest to extract from data, even from LIGO data. And I believe you did an exercise about it yesterday. So I think we'll stop here. So tomorrow I'll be talking about the detection of gravitational waves. So we'll derive the response of a detector to a gravitational wave signal. And if I have time, I'll start talking a little bit about the astrophysics and discuss the LIGO results. Thanks.